Welcome to our quantum deep dive. Today, we're jumping into the world of a true pioneer, an architect of the quantum computer, Michel Devoret. And we're basing this entire deep dive on a fantastic and comprehensive essay by Jorg O. A. Schnippet.
All right, so here's our game plan. We're going to start with the big picture, what this second quantum revolution even is. Then we'll get into the weeds of the technical challenges, introduce you to the man himself, and walk through his groundbreaking work. After that, we'll see how those ideas exploded out of the lab, and finally, we'll reflect on his incredible legacy.
Okay, so to really get a handle on what Devoret accomplished, we've got to set the stage. He didn't just work in a vacuum. He was a key player in what's now called the second quantum revolution.
So what's the difference? Well, think of it like this. The first revolution was about understanding quantum mechanics on a massive statistical level. It gave us amazing things like lasers and transistors, but we were really just harnessing the collective behavior of billions of particles. The second revolution, though, is on a whole different level. It's about reaching in and grabbing a single quantum system, an atom, an electron, or in this case, a circuit, and controlling its state with absolute precision. We're not just observing the quantum world anymore, we're engineering it.
So how in the world do you actually build one of these quantum machines? Well, the platform that's gotten a ton of traction uses superconducting circuits. But this comes with a huge, almost philosophical challenge. How do you get something you can actually build and hold in your hand to follow the totally bizarre rules of quantum mechanics?
Well, the answer, the magic ingredient, is something called the Josephson effect. It sounds complex, but the core idea is pretty wild. Imagine you have two superconducting materials, and you separate them with a razor-thin insulating barrier. Now, classically, that should just stop the flow of electricity, right? But in the quantum world, pairs of electrons, these things called Cooper pairs, can do something impossible. They can tunnel right through that barrier as if it weren't even there. This effect is the key that unlocks the door, allowing a large man-made circuit to act like one single quantum entity.
And this is where the genius really kicks in. Scientists, including Devoret, realized that by carefully engineering these little junctions, you could create artificial atoms. I mean, how cool is that? These aren't atoms you'd find on the periodic table. They're circuits that behave like atoms with their own unique controllable energy levels. And if you can control those energy levels, you can create a qubit, the quantum version of a bit, which can be a 0, a 1, or both at the very same time.
So you've got this incredible theoretical tool, this Josephson effect, but who was one of the key figures who actually rolled up his sleeves and helped tame these wild quantum circuits? Let's meet the mind behind the machine, Michel Henri Devoret.
Devoret's journey is just a fascinating story of being in the right places with the right people. He starts in the elite academic circles of Paris, mentored by a future Nobel laureate. Then he moves to UC Berkeley to work with John Clark, who was an absolute master of making ultra-sensitive, low-noise measurements, a skill that would become crucial later on. And finally, he lands at Yale, where he establishes the group that would go on to change the face of quantum computing.
So, Devoret's career is just studded with these major breakthroughs. It's hard to pick just a few, but we're going to focus on three that were absolutely fundamental. These are the pillars that really transformed quantum circuits from a physicist's curiosity into a practical engineer's toolkit.
Okay, first up, and this one is a real mind-bender. Devoret was a pioneer in proving that quantum weirdness wasn't just for subatomic particles. He demonstrated that a property of an electrical circuit, its quantum phase, could actually tunnel through an energy barrier, just like an electron. This was a monumental discovery. It meant you could build something big enough to see and still have it obey the strange laws of quantum mechanics. It wasn't just theory anymore, it was an engineering principle.
So, his second huge contribution solved a make-or-break problem, measurement. You see, reading the state of a qubit is ridiculously hard. The signal it gives off is incredibly faint. It truly is like trying to hear a whisper in a hurricane. If you use a normal amplifier, the noise it adds completely swamps the signal you're trying to measure. Devoret and his team designed the ultimate solution, a quantum-limited amplifier. It's like the world's most perfect microphone, designed to boost the signal while adding the absolute bare minimum amount of noise that the laws of physics will allow. Without this, we'd be flying blind.
And that brings us to his third, and probably his most famous, breakthrough. The problem with early qubits was that they were just too fragile. They were brilliant, but they were like delicate soap bubbles. The slightest disturbance from the environment, and pop, their quantum state would collapse. The solution was the transmon qubit, which he co-developed with his colleague Robert Schoelkopf at Yale. It was engineered from the ground up to be robust and less sensitive to noise. The transmon wasn't just another qubit, it was the workhorse the field had been desperately waiting for. And the magic is all in the math. Now don't worry, we're not going to have a quiz on this equation. The key insight is all about the relationship between two numbers, EJ, the Josephson energy, and EC, the charging energy. What Devoret and his team figured out was that if you design the circuit so that EJ is much, much larger than EC, the qubit suddenly becomes way more resilient to the electrical noise that was killing the previous designs. This one simple-looking tweak in the design parameters made the coherence time, how long a qubit can hold its quantum state, jump up by orders of magnitude. It was an absolutely brilliant and elegant solution. And this is the part of the story where things just explode. These breakthroughs were so powerful and so practical that they didn't just stay in academic journals. They created a massive ripple effect that spread from the lab bench right into the heart of the tech industry, really kickstarting the commercial quantum computing race we see today.
Yeah, Devoret wasn't just a scientist in a silo, he was a community builder. He helped turn the Yale Quantum Institute into a global powerhouse. And it is no exaggeration to say that the Transmont design is the bedrock of today's leading quantum processors. I mean, both IBM's quantum computers and Google's Sycamore chip, the one famous for that quantum supremacy claim, are built directly on this architecture. And beyond that, he trained the next generation of leaders in the field, people who now drive research at these very companies and at other top universities. It's an incredible legacy of mentorship.
So when you step back and look at the whole picture, what is the lasting impact of all this work? It's not just one invention. It's about how he connected the dots to create a clear, logical pathway that took an incredibly abstract idea and turned it into a real, tangible technology.
You can really think of his legacy as a complete roadmap. First, he provided the fundamental proof that this was even possible with circuits you could build. Second, he created the super-sensitive tools you needed to actually measure them. Third, he co-invented a robust design, the Transmon, that industry could actually build and scale. And finally, in doing all that, he bridged the critical gap between pure physics and applied engineering. He showed everyone how to get it done.
But beyond all the incredible technology, Devoret was also deeply reflective about its impact on the world. This quote just captures it perfectly. He understood that as scientists, their responsibility doesn't end at the lab door. He knew that when you build machines this powerful, you have an obligation to start a broad, open, public conversation about what it all means.
And really, that leaves all of us with the critical question for the future that he helped create. As these machines become more and more powerful, how do we make sure this quantum revolution is a responsible one that benefits everyone?
A powerful thought to end on for sure. That's all we have for this explainer. Our sincere thanks again to Jorgo Schneeppot for the incredible research that made all of this possible.
For more of his work, you can visit schneeppot.de. Thanks for watching.
Schneeppot.de is a private project by Jorgo Schneeppot dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.